We've talked about the comparison test, and at the end of that video I indicated that there might be instances where it really feels like the comparison test is the correct one to use, but our inequality doesn't face the direction that we would like. And in that case, it's often a good idea to continue with the same two series that you're trying to compare with terms a sub k and b sub k, but instead apply the limit comparison test. Here we take the limit of the ratio of those terms, and let's say that that limit is equal to c. As long as c is not equal to 0 and not infinite, then you can say that the two series behave the same. They either both converge or they both diverge. One thing to point out, it doesn't matter in taking this limit if you put a sub k on the top and b sub k on the bottom, or vice versa, because if you have a limit c that sits between 0 and infinity, then 1 over c, or the limit of that reciprocal, will likewise sit between 0 and infinity. So it doesn't matter which one goes in the numerator and which one goes in the denominator. So I briefly mentioned in the video on comparison test that we looked at the sum where we had k plus 1 over k squared. And if I change that plus to a minus, as I've done here, then the series that I would like to compare to, which again, taking the highest exponent in top and bottom, would give me k over k squared, which is the same as the sum of 1 over k. This series diverges as a p series with p less than or equal to 1. But this provides an upper bound for the series we started with, so the comparison test would give us no information. So let's take those same two series, one of which we know that it diverges, the other we're trying to determine, and apply the limit comparison test. So in this case, it doesn't matter which one I'm thinking of, AK or BK, I'm just going to take one of the terms, one of the series terms, and divide it by the other. And this is the same thing then as multiplying by k over 1, and doing that we get k squared minus k over k squared. Notice that I can look here, because the degree of the top and bottom is the same, I can just take the ratio of leading coefficients, which is just going to be 1. This is my c value, and what matters here is not so much the number I got. If I had gotten 1 million or 0.0001, or as I have here 1, all that matters is that that limit is between 0 and infinity, which means that the test is now applicable. This means the two series that we're looking at behave the same. We know that one of those series diverges. So in fact, this tells me then that the one we started with terms k minus 1 over k squared, that behaves like the other series. So this series diverges as well. And here I want to reference that the test we're applying is the limit comparison test. For another example, we can look at 1 over 2 to the k minus 1. Again, that almost looks like a geometric series, which would make me think of using the comparison test, where I'm focusing on this part here. So the sum of 1 over 2 to the k, which is 1/2 all raised to the k, I know that that sum converges because it's geometric, and the absolute value of r, which is 1/2 here, is strictly less than 1. But this converging series is smaller than our series. Think about the denominator on the left is smaller, so the whole fraction would be larger. So I can't, again, use direct comparison to come to any useful conclusion. So here I'm going to, again, jump into applying limit comparison test, taking the terms of one of these series and dividing by the terms of the other. And again, this division can be represented as multiplying by the reciprocal, where I end up with 2 to the k over 2 to the k minus 1. Now we could use L'Hopital's rule here, but perhaps it's simpler to just divide everything, top and bottom, by 2 to the k. The top becomes 1, and the bottom becomes 1 minus 1 over 2 to the k. But now it's a lot easier for me to see that this limit then overall approaches 1. Again, the fact that it approaches 1 only matters to me in that 1 is in the approved interval from 0 to infinity. So that tells me that the limit comparison test is applicable and these two series behave the same, meaning that the sum of 1 over 2 to the k minus 1 converges by the limit comparison test. So the last thing I want to mention here is why can't c equal 0 or c equal infinity? C representing the limit of interest here. So you really want to avoid, in the instance that you get 0 or infinity, you can't make a conclusion from the limit comparison test. So the best way I feel that I can indicate that that's true is to think about the instance where, let's see, so what if c were equal to infinity? If a sub k were 1 over k and b sub k were equal to 1 over k squared, then in this instance, if you were to take the limit of a sub k over b sub k, that's the limit of just k, if you simplify that, and that goes to infinity. And here we get that the sum of a sub k diverges and the sum of b sub k converges. So I have an example here where the limit that we're looking at is infinite and the series behave differently. Now, you might then ask, well, perhaps if the limit is infinity, that automatically means that they have the opposite behavior, and that's actually not true. So just to kind of round this out, if we had a sub k equals, let's say, 1 over k squared, and b sub k equals 1 over k to the 4th, and taking the limit of ak over bk here, that's equivalent to taking the limit as k approaches infinity of k squared, which is infinite. So it's another example where our c value is infinite. But in this case, both series that we started with converge. So what I'm trying to explain here is that now we've seen examples where we can have the limit infinity, but the series behave differently. The limit is infinity, but they behave the same. So kind of the takeaway from this is that if the limit is infinity, I have no idea what I can conclude. So I have to use a different test. Turns out the same exact thing happens with 0. One way to think about that is if I swap the roles of AK and BK in these examples, the limits would be 0, but we'd have the same conclusion. So this is just a cautionary portion. Just there are some assumptions that we're making when we're using the limit comparison test, and if I ignore those, then I can really end up with a faulty result there. So really being careful to actually check that limit, and we want to avoid getting the extreme cases of 0 or infinity.